Greetings. In this talk, I will provide an update to our work on the simulation of fuzzy dark matter systems, in particular, how we are implementing baryon systems that can interact with the fuzzy dark matter. For colleagues from the wider fields of cosmology, I would also strive to give you some motivations about the FDM models in general and the typical tools used to study them numerically. At this conference, I guess, to most of us, the existence of dark matter is motivated by observational cosmology. It starts with the galaxy rotation curves, and as we look at bigger and bigger scales, we realize some extra masses are needed to explain the universe as we see it, or how it comes to become the way we see it. And of course, people have searched corners of physics or imagined other corners of physics we have not yet looked, where extra masses can be created through mechanisms. And for us, we focus on the possibility that dark matter is composed from light bosons, in particular ultralight axions, which might be given rise to from string theory. In our case, ULDM just simply refers to a bosonic scalar field that couples the gravity minimally and has a single particle mass of 10 to the negative 22 electron volts in that ballpark. The particular bonds are sometimes contested, but it's 10 to the negative 22 has been the accepted number through which we model things. At such a small mass, and of course, at such a huge occupational number for any spatial volume, it is sometimes more practical to just regard ULDM as a quantum mechanical existence, to model the whole thing as a wave function. So the small-scale behavior of ULDM is naturally modulated by wave interference. And arguably conveniently, suspiciously, it explains why we do not detect dark matter particles, because being so light, it wouldn't cause any detectable scattering or collision effects on Earth-based particles. And of course, the de Broglie wavelength is typically thousands of solar systems across. This particle does not care about structures at scales that are accessible to humans. Which, of course, is one of the fundamental motivations of ultralight dark matter models, is that structures at the center of galaxies formed through UODM dynamics is naturally core-y, that is smooth and flat, as opposed to the canon CDM models, which usually give you a cuspy or divergent core density in the middle of galaxies. Observations favor the core, while CDM struggles to explain how you can modify the cusp into a core. Somewhat relatedly, as this talk is being prepared, there has been the reports from observational group that it has detected signatures in gravitational lensing due to modulated by wavy dark matter patterns. I believe there are more qualified people in the audience to discuss this work, but I'm mentioning it for the seeming relevance from the observational side to everything. A scalar field minimally coupled to gravity that just, you can write down the action. Of course, we take the axion potential to only contain kinetic term with no higher degrees of self-interaction. There can be simple modifications to include those. And we take the low energy limit of that, which simply brings back the Schrödinger equation, where the wave function now generates mass through Poisson equation, like this. This makes everything nonlinear, but fun to solve. And of course, we can through the gravitational potential, couple other things, or by modifying the definitions of the gradients, we can account for more realistic cosmology, such as the expansion of the universe or the entire evolution history through the scale factor. When you talk about Schrödinger-Poisson equations being nonlinear PDEs, you talk about Schrödinger-Poisson solitons. They are the balanced states between a clump of dark matter self-gravity and quantum pressure, which is mostly induced by the uncertainty principle of quantum mechanics. Literature has reported that these structures may form dynamically inside a halo. Some argue it's so robust you can take away a soliton and a new one would pop up in this place a few cycles later. And you can solve Schrödinger-Poisson equation numerically to obtain the general radial profile, and we can scale them according to the total soliton mass or the axion mass. In general, lighter solitons are puffier, bigger, and less dense. Solitons have been the main interest of my ULDM work. In isolation, people have been able to decompose its oscillations into quasi-nova modes. Luna Zagorak, whose paper you can read here, has laid the foundations for this. And slightly less perturbatively, we realized that quantum pressure supporting all the soliton structure is rather weak. So if you expose a soliton to external potentials, its shape and dynamics might be profoundly different. Another useful tool we have is the Mandolin Picture of quantum mechanics. It's simply saying we regard the wave function itself as encoding information for various properties of a fluid. So we see the amplitude of the wave function as the square root of a density field, and we see the gradient of the phase as a velocity field. It is quite powerful because it simply simplifies solving Schrödinger-Poisson equation into essentially solving fluid mechanics equations with some odd pressure terms. And I actually came across this work at last year's Cosmology from home. You can even generalize in the opposite direction, i.e. you can use an effective wave function in a certain sense to model other fluids like collisionless CDM. So we've been simulating solitons. We've been solving the nonlinear Schrödinger-Poisson equations. Here's just 4 solitons orbiting each other, doing their thing. But this picture sort of also hides under it a few points one need to be careful about when solving Schrödinger-Poisson equations in this picture. One is because velocity field is gradient of a phase. If the gradient is too sharp, then and you discretize the system when you solve it, you will get aliasing. That means there is a speed limit, not because of physics, just because of numerics. And when you store a phase information for a complex number whose modulus is tiny, it's not really numerically stable. If it's 0, you cannot do it at all. And if it's small, it might become random pretty fast. And of course, talking about the phase again, it's velocity fields you induce from gradient of a phase, of course, are spinless, so we wouldn't have spinning ULDM structures. Well, we can have a soliton orbiting somebody in a circle, but the solitons themselves are necessarily not spinning. So how, or will there be angular momentum exchange we cannot capture with this model? It's also something quite keen to figure out. So let's come back to the math. and talk about how we numerically approach this. From the start, we know we want to advance the Schrödinger-Poisson equation mostly through pseudo-spectral methods. But sometimes finite difference methods work too. And of course, they introduce different kinds of cutoffs. They favor different kinds of features, but they have also other differences. The most particular one is that pseudo-spectral method, being Fourier-based, assumes periodicity across the domain, so you can't use it on just any wave function. You have to use it over the whole simulation domain. And as I've been doing this for a long time, we do notice the cost of simulating everything at the same resolution over the same time steps. That is, advancing steps over empty space in your simulation is a waste of resources. So our strategy has been to try to employ adaptive mesh refinement and perform pseudospectral methods on the root grid with finite differences on the refined grids up to as many levels as we need. This work is based on NIX, which is an astrophysical cosmological simulation code written by LBA-NL in the past decade that natively supports multiple fields and accounts for many kinds of physics with adaptive mesh refinement. And of course, our friends at Göttingen a few years ago have modified NIX to work with the Axionyx by introducing the pseudo-spectral solvers on the root grids. So we take Axionyx and look at what's removed when they were simplifying NIX and adding back or adding other physics, of course, grid-based physics at this point, to Axionyx so they can talk to each other by gravity. We haven't yet included cooling mechanisms or star formation or anything, or ionization, but these can be implemented. And both the axions and the gas can trigger grid refinement, which I think is pretty cool. We're trying to also build tools that are easy to pick up for our colleagues in the greater field. So if you're from other cosmological simulation backgrounds, the variables should be able to be translatable rather easily in our finished product. The simulation situation you have looked at is just the spherical collapse. You take a clump of UODM and gas and just let them evolve in time under its own gravity within an expanding universe. As we speak, in mid-June, the first high-resolution runs are still being conducted. But on my own machine, I have the following movies to show you. Here's the density field, a slice of the density field of the ULDM as it undergoes gravitational collapse. As the box gets bigger and bigger, of course, things get concentrated by that, but also it gets concentrated because of gravity. And you can see the waviness of dark matter manifesting in some of the bounce back waves. Corresponding to this run, there's the baryonic physics gravitational collapse. You can also see the structure gets denser, more compact, and over time. This run has, well, this video has more frames, so things happen more slowly. To better capture the movies, I guess, we also took the radial average of densities over time. On the left is the dark matter density, on the right is the baryon density. You can see that as time goes from blue to orange, all the densities at the core increase dramatically, while other finer structures can be noticed in the baryons, which I think are things more worth exploring. This literally marks the first efforts. We will be running more high resolution runs for the spherical collapse. And of course, we might also set up bigger boxes with more realistic initial conditions. And we want to systematically compare our simulations with previous runs widely reported in the literature that only concern ULDM and highlight how much baryon really alters the system's evolution. And of course, as we said before, we want star formation and feedback in the code to make these balls of gas look more like a galaxy. We also intend to compare and extend with other similar works in the direction. Just recently I come across this paper that simulated a star formation within the FDM background using completely different numerical tools. But I believe to be able to match this paper's work would be a very good start point to advancing our own understanding of FDM physics within a baryonic context. So, in summary, ultralight dark matter is really interesting as a dark matter candidate. We model its wave behavior with a wave function in the Mandolin Picture, and this leads to a rich array of interesting dynamics. And I think coupling FDM simulations to hydro codes is really an essential step in considering in constructing testable models of ULDM properties and bringing our predictions one step closer with human doable astrophysics. This work is done over my last year at the University of Auckland. All the calculations are performed on New Zealand National e-Science Infrastructure NESI, and I'm giving this talk supported by the infrastructure of Perimeter Institute in Ontario, Canada. Thank you very much for your time.